All right, so as we look at this last page, we're going to find the limit at a point of discontinuity. So this looks a little different than example 8 from yesterday, right? Example 8 from yesterday had inequality signs over here. We have a not equals to and an equals to sign. So we're going to go ahead and graph this piecewise function. And we're going to use algebra and our calculator. So I'm going to start off with graphing just this part right here, the x squared minus 9 over x minus 3. And you can put that into your calculator. And if you put the whole thing into your calculator, so x squared minus 9 divided by x minus 3. Make sure that you use parentheses for both your numerator and your denominator. And if you hit graph, what do you see on your calculator? A linear line, right? And here's why it's a line. If I use my algebra, and so let's take and say that we've got y equals x squared minus 9 over the x minus 3. Can't I factor the x squared minus 9? Yep, so I get x plus 3, x minus 3, all divided by x minus 3. And so magic happens. Don't the x minus 3's cancel? And we're left with x plus 3. So really the graph that you see on your calculator, when you put this into the calculator, you're really seeing this, because algebraically we can cancel out the x minus 3's. Technically, there's a vertical asymptote where? So there's a vertical asymptote, that's a y, and you're the first person to say it correct today, at x equals 3. It's not just at 3, it's at x equals 3. So technically, right here, that's where our vertical asymptote goes. Right where 3 is. And it just so happens that that's the number that we're going to be approaching when we find our limit. So this graph crosses the y-axis at 3, the x-axis at negative 3. And then I can't actually plug in, because I want to know what value it is as it crosses this vertical asymptote. Well, obviously I can't plug that value into here because it makes it undefined. But can't I plug that value into here? Right? And what is 3 plus 3? I'm going to plug this value in because I'm trying to find out where it is at 3. What's 3 plus 3? 6. Well, technically, there is an open circle at 6. Right here. This is where 6 is. So I'm going to connect. You use a straight edge. I can't. But here I'm connecting. And then it goes on. Whoops, that wasn't very good. All right, so that's that equation, x squared minus 9 over x minus 3, and we've allowed for the hole in the graph for the undefined portion. So that takes care of this.
What was it? That a graph of?
This one right here. Just that piece, not this piece. And so notice that it says we want this graph everywhere but where x is at 3, because that says everywhere but x cannot equal 3. Bless you. Well, that's what that hole is showing. It's showing everywhere for x, but x can't equal 3. This is saying something different. Normally the graph of y equals 2 would be right here. A horizontal line going through the y-axis at 2. But it says only where x equals 3 do we want y to be 2. So this is actually an ordered pair. This is actually just a point. Because it's restricting us to just an x value of 3. And at the x value of 3, the y value is 2. So we're going to have a closed circle right here, and that closed circle actually plugs this hole here. And visually, that is your point of discontinuity. So it's not a jump like we had in example 8 before this. This is continuous all the way along, with the exception of this one little piece. We have a hole here that's plugging it. So you're going to find that this overall actually has a limit, whereas example 8 did not overall have a limit. So we're going to find the limits, because it says find the limit as x approaches 3 of the function. And so, and then we're going to prove that the function is discontinuous. So emphasis on the word prove that the function is discontinuous. Well, in order to do that, we're going to find the limit of each of these items here separately to prove this part. So here we go. The limit as x approaches 3 of x squared minus 9 over x minus 3. So just that portion. Let's look at that limit. So as we approach 3, this is our 3 here. As we approach 3 from the right, what's my limit? As we approach 3 from the right, isn't that value right here? Because here I am approaching it from the right. The graph is coming from here, and as I get closer and closer to 3, the graph gets smaller and smaller and smaller, and it finally reaches that y value of 6. So the right-hand limit is 6. What's the left-hand limit? As x approaches 3 from the left, this graph is going up and up and up, and it approaches a y value of what? 6. So it does have an overall limit of 6. And if you think about it, doesn't the overall f of x graph also have a limit of 6? Because that hole makes no difference. If I'm approaching 3 from the left, the y value is 6, no matter whether that hole's there or not. And as I approach 3 from the left, the y value is 6. So the function f of x also has an overall limit of 6. So the function itself has a limit, 6. But we're trying to prove that there's a point of discontinuity. So I'm going to now take the limit of this other piece separately. So let's find the limit as x approaches 3 of 2. Isn't this the limit of a constant? What's the limit of a constant? The constant itself. So isn't that limit 2? So we've just proven that there is a point of discontinuity right here by taking the limits of the separate elements, if you will, and see that they're different. Since they're different, there must be a point of discontinuity. So since these do not agree, there is a point of discontinuity at x equals 3, because that's what we're approaching. So if you want to prove a point of discontinuity, find the limit of each of the separate elements of that piecewise graph. If they don't agree, there must be a point of discontinuity, whether there's a jump in the graph, a hole in the graph, something of that nature. This graph does have an overall limit of 6, where the graph yesterday of example 8, it does not have an overall limit because that graph's left and right hand did not agree. Yes?
Why couldn't the limit be 3?
Why is it not 3? Because as I approach this entire graph right here, so taking into account the point here and that whole graph, as I approach 3 from the right, as I get closer and closer to 3, even right here at 3.5, isn't the y value all the way up here? And the y value continues to be all the way up here, but as I get closer and closer to 3 from the right side, the value of the graph approaches and gets closer and closer to a value of 6. It will never reach a value of 6 because x cannot actually be 3. Okay? And then as I approach 3 from the left side, as I get closer and closer to 3, the y value climbs and gets higher and higher and higher and higher, and it approaches 6 as well. Again, the only value that x can be at 3 is that y value of 2, only because of this right here. And so the overall graph does have a limit of 6. This hole right here makes no difference. So as I approach it, we don't just all of a sudden drop down to 3. Okay? Because if you look at your table of values, if you put 3.1 in, it's going to be really close to 6. It's not going to be close to 2. Does that make sense a little bit? Okay. Any other questions before we move on to investigating limits with infinity? None? We're good? Isaac?
I was watching, but how did you get 6 on that?
For the limit? So again, as I approach 3 from the right, as I get closer and closer to 3 from the right, that limit is all the way up here. So at 5, my limit is fairly high, whatever that is. So I could plug it into my calculator. So if you go to your table on your calculator, so do second graph and you get your table. If you put in 5, you get a value of 8. So all the way up here at 5, I had a value of 8. If I put in 4, I get a value of 7. I can't put in 3, but I could put in 3.5. That's going to get me closer to 6. So instead of 7, it's going to be like, I don't know, 6.5, let's say. And then as I get closer and closer to 3, that y value is going to approach and get closer and closer to a value of 6. Same thing from the right side. No matter what I plug in, as I get closer and closer to 3, that value for y is going to keep climbing and getting higher and higher and higher until it finally approaches a y value of 6. It doesn't matter that this point is here at all. Okay, so then let's go on and look at example 10. We're going to investigate limits as x approaches positive and negative infinity. But before we do that, let's talk about a couple of situations where we have right and left-hand limits of infinity and negative infinity, because you had a problem, which you never asked me a question on, from Friday's homework, where you had... it was actually exactly like question or example 4b. So if you look at example 4b, see how the right and left hand limits went up to positive infinity? What did we say about those limits? Both the left and right hand agreed they went to positive infinity, but what did I say about the overall limit? The limit did not exist because a limit of infinity is not a real number. It's unbounded. Well, your book will kind of waffle on that. So let's look at the following example. That's an arrow. So let's look at the limit as x approaches 0 of 1 over x squared. So if you put that into your calculator, 1 divided by x squared, you're going to get the following graph. You're going to get a graph that looks like this. Those are arrows on the end there. And so this looks just like that example 4b. As I approach 0 from the left and from the right, what is happening to the y values? As I approach 0 from the left and the right, what's happening to the y values? They're increasing without bound. So from the left, it's approaching positive infinity, and from the right, it's approaching positive infinity. Now I need you to understand that your book sometimes will say because, and so think of it this way, because in theory, if the left and right hand agree, then that's the limit. Well, don't the left and right hand agree? So sometimes your book is going to say that that limit is infinity, when in reality, I want you to clearly understand that the limit does not exist. However, or we could say that it is positive infinity. But I need you to understand is positive infinity sometimes, according to your book, because of that theory that the left and right hand agree. But the true definition of a limit is that it has to be a finite number. And is that a finite number? No. So when you go into Math Excel, if undefined or does not exist doesn't work for your answer, then put in infinity or negative infinity, whatever it happens to be going towards, and then that might be why your answer is wrong. I will be lenient and accept both. And if you want to be on the safe side, you can just put both does not exist or positive infinity. But bear in mind that if one of your ors is not an acceptable or, then you're going to lose partial credit. So bear that in mind. Let's look at one additional one. So the other one we're going to look at is the limit as x approaches 0 just from the right side only of the natural log of x equals. And so if you plug that into your calculator, you're going to get the following. And so you'll see that as we approach 0 from the right side, because we can't approach it from the left because the domain of x does not, the domain of x has to be greater than 0 for the natural log function. So we can't really approach it from the left. We can't plug any of those numbers in. So as we approach it from the right, what is happening to the y value? It's approaching negative infinity. As I get closer and closer to 0, so as this gets closer and closer to 0, this line here is going to get closer and closer to that y-axis. It'll never actually touch the y-axis. And if you put into your table of values, if you start with 1 and then put in 0.5 and then put in 0.2 and then put in 0.1, 0.001, 0.00001, 0.00001, you get the picture. You're going to start to see that value for y increase negatively. It won't increase very quickly at first, but it will start to get bigger and bigger negatively. And so this theoretically can have a limit. That's a terrible infinity, but it can have a limit of negative infinity. So based upon what we just discussed, the limit can be negative infinity. And the only reason why I'm saying that is based upon what we just discussed here. Technically, that limit does not exist, though. Agreed? Agreed, but oftentimes in calculus, we need to look at that limit as being negative or positive infinity, whatever the case may be. But I want you to write yourself a note over here to the left, so you can write it along this, well, let me get my different pointer out here that points in the correct direction. There we go. So put a note out here to the left. I'm not going to write it. Well, I guess I could. I can turn my paper, can't I? Ha. What a great skill that is. All right, so put the following note out here. Note to self. Limits are always real numbers so technically a limit of positive or negative infinity does not exist. So not to try to confuse you, but I just need you to understand what your book is doing. And sometimes they'll give you the answer as infinity, and sometimes they'll give the answer as undefined. You need to understand why they're doing that. Okay, so then let's look back at our problems. All right, so let's actually look at this particular problem right here. Oh, wrong direction. Let's try that one. There we go. So for this one, we've used this a lot, haven't we? But this time, instead of approaching 0, we're going to approach positive infinity and negative infinity. So let's go ahead and draw that graph. So I'm going to separate these. So we're going to draw our graph. I want you to do something, though. I want you to put into your calculator the sign of x divided by x. And we've seen this before, and then I want you to zoom in on it one time. zoom in on it once. But if you looked at the unzoomed version, you can see that it crosses the x-axis somewhere. And so I'm going to change my window for the x min to be -5. So go to Window, put in for x min -5, and for x max put in 5, enter, and then hit your graph again. What do you see happening? Where is it crossing the x-axis? Well, it looks like 3 and -3, but we know it's not really 3 and -3, right? It's radian measure. But somewhere here and here, it is, I swear I hear a baby crying in the hallway, don't you? The weirdest things are happening lately. All right, so it looks like our graph looks like this. But let's look at our table of values. I want to see, as I approach x, as x approaches positive infinity, so we're going to the right. That means our numbers are increasingly getting bigger and bigger and bigger. So if I had my table of values, so you're going to go to your table of values, and we're going to put in the number 1. What do you get? A small number, don't you? So you get 0.84147. Well, I want to go to positive infinity, so I want my numbers to get bigger. So I'm going to then put in 10. So if I put in 10, I now have negative 0.0544. Now I'm going to put in 100. All of a sudden, oh no, I still have a negative. So I have a negative 0.0051. So what do you see happening here? What do you see happening here? It crossed the x-axis, right? Okay, and then it's getting negative, but it is negative, but it's getting close to what number? 0. Okay, so an interesting thing occurs when we hit 1,000. At 1,000, we actually get a positive, and yours is showing in scientific notation 8.3 times 10 to the -4, so it's really positive 0.00083. All of a sudden, it crossed the x-axis again, didn't it? And it went positive. But this is still really close to what number? 0. Well, let's put in 10,000. Now we get -3 times 10 to the 5, so it's negative 0.12343. What number is that really close to? 0, and it's also negative again. So we've gone across the x-axis again. Isn't this waffling back and forth across the x-axis like a normal sine curve would? True or false? Okay, but my point is, even though we have this waffling behavior, it's not oscillating. It is still getting closer and closer and closer to 0. As I keep crossing the x-axis up and down, it's getting closer and closer to 0 each and every time. So as I approach infinity, what is the graph getting closer to? What's its limit? 0. So here's how we write that. So the limits as x approaches, and I'm going to make it really clear that I'm approaching positive infinity by putting a plus infinity there. Your book likes to leave it off, but I'll always put the plus there. And I'm just going to put f of x here. It is approaching 0. What do you think is going to happen when we go to the left? It's going to be the same thing, because it's going to have that same waffling behavior because it's symmetrical. And so we get the limit as x approaches negative infinity of the function, we also get 0. This actually has there is not an overall limit of 0 then, because we're not approaching a particular number. So you can't say, well, then the overall limit as x approaches what? I mean, we're approaching positive infinity and negative infinity. That's not an actual number that we can grab a hold of and put a vertical asymptote in and say, okay, this is what we're approaching to the left and the right. Agreed? Aren't these two different directions? So these are two different, very finite limits. So it does have a limit, but this is called, this is our limit. It's not even really a right-hand limit. It's our limit as we're approaching infinity. This is our limit as we're approaching negative infinity. So there's not an overall limit when we're approaching infinity and negative infinity. It's one or the other. Are you clear as to the difference in that? Okay, and there actually is a limit because our limit itself is a number. It's not infinity. You can approach infinity and have your limit be infinity. You can approach negative infinity and have your limit be infinity. You know, it could also be negative infinity too. So, and technically if the limit is infinity or negative infinity, what is the actual limit? Does not exist, technically. Okay. So questions on that before we talk about the last two? I know, you're like, well, I'm going to let that soak in. All right, so let's talk about, really we only have one more because we've already dealt with 12 before. So let's put this into our calculator, the 1 over x minus 2 squared. You might want to zoom standard so that you get an accurate look to your graph. Is there a vertical asymptote to this? Is there a vertical asymptote here? Is there any place that makes this undefined? 2, so x cannot equal 2. So we have a vertical asymptote at what? At x equals 2. So when we graph this, this is our visual limit that we're approaching here. It also happens to be our vertical asymptote. How handy is that? And then our graph should look like this. The y value can never be negative because we're squaring that denominator. Go away. So, look at what we're approaching. We're approaching 2, and we want to approach 2 from both the right and the left. So let's look at those individual limits. So the limits as x approaches 2 from the right of 1 over x minus 2 squared is equal to. So as I approach 2 from the right, what is happening to the y value? So as I get closer here, what's happening to the y value? It's approaching positive infinity. So our limit is indeed positive infinity, which technically isn't a limit, right? But we're going to go with it. And then as I approach 2 from the left, what's also happening? Same thing. So as I approach 2 from the left, it also equals positive infinity. So, therefore, because those agree, therefore, what is your book going to say? Yeah, the limit as x approaches just plain 2, because that's, we've now evaluated the right side of the limit, we've evaluated the left side of the limit. I still say that the limit does not exist. I still maintain and hold that true, or your book quite possibly will say positive infinity, right? Because that left and right hand limits agreed. And if you want to, be on the safe side and put both down there, that's fine. And then the last one, we've done a lot of work on this last one, haven't we? I mean, we've already talked about this. And the only difference between this one and example 10 was we're approaching a different number. So here's the graph. Okay, but as we approach 0 going from the right and from the left, what is the limit ending up being? Knowing that there's a hole in the graph there, right? So as we approach this graph from the right and the left of 0, what's the limit? Oh, I totally put my numbers in the wrong spot there. Oh yeah, okay, darn it. Let's say that this is a half, and that's 1, right? Is that better? So it's approaching what number? 1. Any other questions before we finish this?